All right, it's my pleasure today to introduce Dr. Luigi Bassini for the Theoretical Astrophysics seminar. Dr. Bassini did his master's in Trieste under the supervision of Professor Borgani on the Lagrangian hydrodynamic schemes of cosmological simulations. And then that was in I think in 2017, and then for the last 3 years, he worked on his PhD, which he has defended, and he also did this with Professor Borgani, also in Trieste, working on a few things that he's going to talk about today. And yeah, I want to give the stage to Dr. Bassini.
Yeah, thank you, Robert, for the presentation. Yeah, actually, I think I still have to discuss in February my PhD defense, but yeah, the PhD is finished. Anyway, thank you first of all for having me here, just giving me the possibility to present myself a little bit. So today we'll talk essentially on what I worked during the last year with mainly with Nela Razia and Stefano Borgani on essentially the star formation history of clusters and protoclusters with cosmological simulations. So yeah, here, can I scroll down? Perfect. So just to start, to introduce just an image of galaxy clusters essentially in a local universe. Well, we all know what galaxy clusters are. So they are the endpoint of structure formation. They are the most massive gravitationally bound objects that we have. And for what concerns the galaxy population, we have a lot of massive ellipticals and bulge dominated galaxies with little to no ongoing star formation, and especially within their cores. So given the low star formation rate that we have in these galaxy clusters actually contribute very low at low redshift to the global cosmic star formation rate density. But of course, this is not true at higher redshift. And the way I think about this usually is by looking at a plot like this. This is essentially the specific star formation rate as a function of redshift or look back time for different elliptical galaxies with different mass, as you see in the labels found from observations. And what you can see here is that essentially the star formation history strongly depends on the mass of these galaxies, so that more massive galaxies formed earlier and during shorter time scale. So since we have in our galaxy clusters a lot of massive elliptical galaxies, we expect also that at higher redshift galaxy clusters and protoclusters are characterized by quite high values of star formation rates. And this is actually what is found in observations. This is a plot by Cato and collaborators of the star formation rate density computed in different clusters and protoclusters as a function of redshift, and also compared to what is seen for the field, so taken from Madao in 2014. And you see that the star formation rate density rapidly increases up to redshift 2 by orders of magnitude. The only, let's say, problem that we have at this redshift is that the number of objects that we have with also information on the star formation rate is relatively low, so around in this case around 10 objects. And this is due to the fact that that it is a little bit, it is quite difficult to detect galaxy clusters at like redshift, because in the local universe usually we rely on the emission from the intracluster medium, which is very often detectable through X-ray emission, but this is more difficult at redshift higher than 2, both because it is difficult to detect the X-ray emission per se, but also because we expect that also a lot of clusters which are not virialized yet, so without strong emission in the X-ray. And also if we rely on the rest sequence galaxies, which is commonly done in the local universe, so to look for over density of red and passive galaxies, also in this case is more difficult to do it at a high redshift, because we also expect that at higher redshift, a higher fraction of galaxies is active, and activity is forming stars. So what it is usually done is to look for galaxy overdensities around rare objects, for example, high redshift quasars or radio galaxies. And this is a quite famous example by Miley, 2006. This is the spider-web complex centered around a radio galaxy, the spider-web galaxy, around redshift 2. But another technique that has been used in the recent years is also to look for overdensity of dusty star-forming galaxies. And this is let's say, useful because, as I showed before, we expect that at higher redshift we have a lot of galaxies in the process of building up their stellar masses. So a lot of star formation, dust obscured, and this concentration of dusty star-forming galaxies can be detected within a large survey characterized by large mean sizes, for example, Planck or SPT, and then these clumps which are observed within this survey can be followed up with higher resolution instruments, for example, Herschel, but also ALMA in the more recent years. And this is another quite famous example. This is the proto cluster by Miller in 2018 at around redshift 4, with a very high star formation rate of around 6,000 solar masses per year. The problem, of course, in this case is that the objects that we found are quite biased, and of course the strict Fourier bias that we have when selecting in the far infrared is that we are selecting the most star-forming region. So that at the end, drawing an evolutionary path of protoclusters from these observations is quite difficult. And in this, to interpret these results, of course, cosmological simulations can be a very powerful tool. But before to interpret the observations, it is also important to make sure that simulations also match the constraints that we already have at high redshift. So essentially, this was the aim of our work. And to do this, we used a set of cosmological simulations developed in Trieste. This is a set of zoom-in cosmological simulations centered on galaxy clusters. And these are selected from a parent box of 1 gigaparsec size, so simulation, dark matter only simulation. And from this box, we selected the 24 most massive clusters, which have a mass higher than 10 to the 15 solar masses, and also other 5 randomly chosen objects, less massive but still higher than 10 to the 14 solar masses. And the initial conditions were produced in order to guarantee at redshift 0 an high resolution region of 5 or 6 virial radius, quite large. And since actually these simulations are quite large, to run them at a reasonable resolution, it was quite painful. So at the end, we were able to run between the 24 massive clusters, only 7 of them, and also the 5 smaller objects, because of course they were less computationally demanding. So the simulations were run with Gadget 3, which is a private version essentially of Gadget 2, which implement an SPH scheme for hydrodynamics with different improvement with respect to a standard SPH, which are described back to 2016. And of course, being a hydrodynamic simulations, it includes all the usual standard models which are implemented to reproduce the baryonic physics, which is not resolved by simulations, including also AGN feedback. So I will not explain in detail all the models that we used, but I will spend a couple of words maybe for the 2 most important ones. So for the AGN feedback and for the star formation model, which will be important in the second part of the talk. So the AGN feedback is implemented according to a Bondi accretion rate formula, so a pretty standard accretion rate formula with this alpha enhancement factor. And this is needed because the Bondi accretion rate is essentially relevant just in case of a hot virialized gas with very low angular momentum. But in the case of chaotic accretion, chaotic cold accretion, the accretion is actually quite higher, so we need a boosting factor that we use, and is fixed around 100 for cold gas and 1 order of magnitude lower for the hot gas. Given the accretion rate, then we have a thermal feedback, which is a fraction of the accreted mass, and depends on two parameters, epsilon r and epsilon f, where epsilon r is the fraction of the mass, which is transformed in radiative energy. And epsilon f is the fraction of the radiated energy, which is coupled to the surrounding gas particles. And of course, we have to tune these parameters, and we do this by matching essentially the local Magorian correlation, so the correlation between the black hole mass and the stellar mass of the hosting galaxies. And the value are this one. Essentially, we have a radiative efficiency of 0.07, which is independent of the accretion rate, while we have two different value of epsilon f depending on the accretion range. So at high accretion rate, a low value, and a higher value at in the radio mode, so at low accretion rates, to mimic more or less what we see from observations. For the star formation model, instead, we use the Springer and Nyquist model 2003, which is quite old but still widely used. And of course, this model is needed because in simulations we do not reach still high enough resolution to resolve molecular clouds, so we need to describe them in a statistical way. And we do this by essentially dividing each SPH particle, supposing that each SPH particle sample a region of the interstellar medium, and each SPH particle is subdivided in a cold phase and a hot ambient phase in pressure equilibrium of one with the other. So the two phases can interact. Of course, we can have cooling, which is given by a cooling function. When we have when the gas cools down, we have high enough density of cold gas, we can form stars following this expression. So the star formation is essentially proportional to the mass of cold gas and inversely proportional to a time scale for star formation, which is given by the dynamical time of the gas particle times a parameter of the model, which is fixed in order to reproduce the Kenika-Schmidt relation, essentially. So the correlation between the gas surface density and the surface density of star formation. And beta is just the fraction of mass, which is in massive stars, so expected to instantly explode at supernovae. And of course, when we have star formation, we also have feedback due to the explosion of these massive stars, which is implemented following this equation. So it is proportional to the star formation rate times beta, so times the fraction of massive star, and times another parameter A of the model, which I describe a little bit later. So essentially, this is also called the self-regulated star formation model, because when you have a high hot gas density, you have a lot of cooling. When you have cooling, a lot of gas, you form stars. But when you form stars, you also have a lot of feedback. The feedback reduces cold gas density, increase the hot gas density, and the cycle restarts over again. So this is essentially thought to describe the quiescent star formation galaxy evolution. So the first results that I wanted to show is essentially a little bit of a summary of the star formation history in protocluster for clusters and protocluster as viewed from simulations. So this is a plot of the star formation rate computed within the virial radius of the cluster, normalized by the cluster mass, and as a function plotted as a function of redshift. So you see observational data plotted as different colored points, where the solid line is a fit to the observational data, and the simulations are plotted instead here as essentially these black squares, and the dashed line is a best fit to our simulations. So essentially, you can see two different effects. The first one being that at low redshift, simulations really tend to overshooting the star formation rate within galaxy clusters. This is mainly driven by the fact that it is quite challenging to quench enough the most massive galaxies that we have, in this case, to quench the BCGs, so the brightest cluster galaxies with massive of around 10 to the 12 stellar masses. And these BCGs contribute to this essentially to the difference that you observe at redshift 0. But at redshift greater than 2, it seems that the situation is kind of reversed, in the sense that simulations seems to underpredict the star formation rate that you have in galaxy galaxy clusters. And I will, in this talk, I will focus on these features, on the difference that we observe at redshift 2. The first, okay, so the first thing that we did is just to try to compare at face value the star formation rate that we have in galaxy clusters within our simulations and the star formation rate that we have in observations. So in this plot, you can see the star formation rate computed within a sphere of 1 megaparsec centered on the galaxy cluster, proto cluster, as a function of the cluster mass when the cluster mass is available. And indeed, when you see these colored bands, is because an estimate of the cluster mass is not possible. And the observational sample is chosen between the protocluster that have coverage in the far infrared wavelengths, because at this redshift, we expect that most of the star formation is in the form of dust obscured star formation. So you see that at least at first glance, simulations indeed seems to have a quite lower star formation rate with respect to the most extreme star formation rates that we have in observations. But of course, we have also a lot of possible sorts of biases. For example, of course, selection effects. As I explained before, these protocluster by Clemens are one example of protocluster selected in far infrared wavelengths. So essentially, they use Planck observation plus Herschel. So these might be the most extreme cases that we can observe. And maybe these are not just for a matter of statistics are not present in our simulations. Few of them also do not have spectroscopic confirmation. For example, the protocluster by Kato. Here, the dusty star-forming galaxies which are observed within these regions have not yet spectroscopic confirmation. And in this case, the upper limit is given by assuming that all these galaxies are within the protocluster, while the lower limit is obtained by subtracting the average values for the field. And in any case, also, if these biases are not important, then we still have large uncertainties, of course, in the star formation rate values that we get from observations. In any case, between all these results, maybe the most striking one is the result from Dammler-Bauer, which are obtained for the spiderweb protocluster. So the spiderweb, which is a bona fide protocluster that simulations predict to be the progenitor of a coma-like structure at redshift 0. So this should be very similar to our cosmological simulation. And still, there is a factor of a few in the star formation rate between these objects. So there are also other observations computed. Essentially, the difference between this plot and the previous one is the region within which the star formation rate is computed. In this case, we have a smaller surface area, so diameter of around 100 kiloparsec, and then integrated on the megaparsec scale along the line of sight. And you see that also in this case, the most forming regions are not reproduced. But in this case, on the pros is that we have also ALMA observations for these objects. This means that we have also spectroscopic confirmation for the galaxies, and we also have observation for the CO emission lines. And this means that we have information on the cold gas content of single sources. So it is possible now to compare not only integrated properties on the cluster size, but also properties of the protocluster galaxies. And the first thing that we compared is the well-known main sequence of star-forming galaxies, which is the correlation between the star formation rate of galaxies and their stellar mass. And you see in the simulations are plotted here as gray circles with the black points representing the median values for our simulations, and results from the field here plotted as red line, and these are observations. So the first thing that you can see is that our simulations are a factor of 3 in terms of normalization below observations. At the same time, we are in a dense environment. We are plotting protocluster galaxies, so it might be that, of course, we are biased low in the sense that in protocluster, let's say everything happens first, so our galaxies are already on their way to be quenched, and this is the reason why the main sequence is lower. However, there are observations, and this is an example by Koyama in 2014, that suggest that there is not such an environmental effect, at least at redshift 2. And in this plot, you can see galaxies from dense environments, from clusters in different extraction regions. So in the core of the proto cluster has red points, and essentially in the outskirts of the proto cluster in yellow. And you see that the normalization of the main sequence is very similar between the field and cluster and protoclusters. So it seems that this difference is not due to environmental effects, and on top of that, you can also see that these green and blue points are the galaxies from the two protoclusters that I showed you before, and these galaxies are scattered around the main sequence observed for the field. So also in this case, it does not seem that there are important environmental effects. And the other interesting feature is that there are a few of these galaxies which are well above the main sequence that can be defined and as starburst galaxies, having an offset from the median value of the main sequence of almost an order of magnitude or even more. And the other thing is that, of course, our simulations are not the only one with this feature. So with a lower main sequence with respect to the data. This is a compilation from few theoretical models, and in particular, you have again the same main sequence for the field, the observed one in red, and different semi-analytical models plotted as dashed lines, and different cosmological simulations plotted as solid lines. And you see that essentially in all cases there is an offset of between a factor of 2 and a factor of 3 between models and observations. The other thing is that also in theoretical models, it does not seem to be important environmental effects. You can see this from the Gaia results, which are results from a semi-analytical model. And you see that the upper blue dashed line is obtained by considering all the galaxies within the simulated box. So this is a good proxy for field galaxies. And the lower one, still blue dashed line, is obtained by considering only galaxies within clusters and protoclusters at redshift 2. And in all mass beams, the difference is never higher than 30%. So also theoretical models does not predict any important environmental effects on the main sequence around redshift 2. So the other important thing to study for the main sequence is also the distribution around the main sequence at fixed stellar mass. This is an example of an observational work by Sargent and collaborators 2012, and they study the distribution of star formation rate at redshift 2 in different stellar mass beams. So you see here plotted as different colors. These are just different mass beams from 10 to the 10 solar masses up to a few times 10 to the 11. And you see that in all cases, the shape is very similar independently from the mass beam. And the other thing that you can notice is that this distribution is not fitted using a single Gaussian, but is better fitted using two Gaussians. So in their representation, the first Gaussian represented the so-called normal star-forming galaxies, where the second Gaussian, they say that these represent the starburst populations. So at least in their work, they used to define these two different populations. This is not, however, very clear, but the clear thing is that you have a broadening of the distribution at higher star formation rate values. And you can measure essentially the fraction of galaxies which are above a fixed star formation rate to have a quantitative estimate of the broadening of this distribution. And this has been done, for example, by Schreiber in 2015. In this plot, you can see indeed the fraction of starburst galaxies. as a function of redshift using different star formation rate thresholds. So the lowest one is in black here, is obtained considering star formation rate, which are 4 times higher than the star formation rate for main sequence galaxies. And in this case, you see that the fraction of starburst galaxies defined in this way is essentially constant and does not depend on the redshift, and is fixed on about 3%. So if you do the same thing for cosmological simulations, this is more or less what you obtain. This is again in yellow, the results from Sargent, so observational results, and these different color lines are the results from these different cosmological simulations. So you have in blue the Dianoga set, which are our simulations of galaxy clusters, and in green and red, you have the results from 2 different cosmological boxes from the Magneticum suite of simulations. The Magneticum refers to cosmological boxes, but have run with essentially the same code that we use for our simulation. So the only difference here is minor differences in the AGN feedback, but other than that, the code is essentially the same. And you can see that in all 3 cases, the simulations are quite well fitted by a single Gaussian, so one component, with the second Gaussian, which is essentially absent. So it seems that really we are under-reproducing the so-called starburst population. And if you compute the starburst fraction as it can be done in observation, so computing the fraction of galaxies with a star formation rate higher than 4 times the star formation rate of main sequence galaxies, you obtain a value which is about actually less than 0.2%, which is at least an order of magnitude lower than what observations suggest. So this is another feature that clearly impact the results on the protocluster star formation rates. So of course, this is only the starburst galaxies are only 3%, but they are actually important if you want to study protocluster. And this is because reproducing, as I will show you in a moment, reproducing the high star formation rates within galaxies enables you to also reproduce observables, like, for example, the sub-millimeter number counts. And the sub-millimeter number counts are important in simulation of galaxy clusters, because we expect to have a lot of dust star forming galaxies within protocluster regions. So this is a recent paper by Lovell, actually a couple of months ago. In this plot, you can see in black the sub-millimeter number counts as obtained from observations, and in orange and blue the results from 2 different cosmological simulations. So from Eagle in orange and from Simba in blue. You see Eagle clearly underpredict the number of sub-millimeter number counts, while Simba is quite well in agreement with the observations. And they claim that these results is possible because Simba better reproduces the high end of the star formation rate function. This is a plot of the star formation rate function, again at redshift 2, where you see the data here in gray, and the results from Eagle in green, and the results from Simba again in gray. You see that Eagle is below the observations at each star formation rate values, quite in agreement with the results that we have seen for the main sequence, while Simba is below observation at star formation rate around 10 solar masses per year, again in agreement with the results for the main sequence, but they quite reproduce well the high star formation rate end of this distribution. And the high star formation end of this distribution are indeed the galaxies that you have here. Indeed, you see in orange and in red the contribution of the star formation rate function from the sub-millimeter galaxies. So reproducing this star formation rate end and essentially the starburst galaxies enable you also to reach quite a good agreement with sub-millimeter number counts. And these results, they claim that is being possible by employing a quite more realistic stellar feedback. So the stellar feedback here implemented usually is defined by this mass loading factor that you can see here on the left. The mass loading factor essentially is the ratio between the mass, which is within winds, so ejected from galaxies, as a function of the star formation rate. So what is usually done in simulations, for example, in our simulation that you can see here in red, is to assume a constant value for the mass loading factor, and we employ a mass loading factor of 2. In any case, high resolution simulations, zoom-in simulation of galaxies, which are the colored points and the fit in orange, suggest that the mass loading factor is actually a function of the stellar mass of the galaxy, so that lower massive galaxies have a higher mass loading factor. And this is the parametric function that SIMBA employed in their simulation. So mass loading factor depending on the stellar mass. And this means that at lower stellar masses, so essentially you can think of also a Tiger redshift, having a high feedback, the feedback ejects more gas in the circumgalactic medium, which then is reaccreted at this lower redshift, enhancing the star formation rate and enabling to reach a better agreement in the eigen of the star formation rate function. Okay, so this is for what concerns the starburst. Again, for the normalization instead of the main sequence, we studied on which is the gas-related quantities that is more related to the underestimation of the main sequence, essentially. And in the plot on the left, you can see for our simulations, again, the main sequence color-coded by the gas fraction on the top panel, and for the depletion time in the lower panel. And you see that essentially we have that galaxies above the main sequence tend to have both higher gas fraction and also lower the depletion timescales. And conversely, of course, galaxies below the main sequence have low gas fractions and also longer depletion times. And this is roughly in agreement, qualitatively at least in agreement with observations. These are observations by Tacconi in 2018. And you see in the upper panel correlation between the gas fraction as a function of the distance from the main sequence, and in the bottom panel, the dependence on the position of the main sequence for the depletion time. So this is in general at least qualitatively in agreement between observations and simulations. But if you study the overall normalization for these correlations, you see that there are actually few differences. This is a plot of again the gas fraction in the upper panel as a function of the stellar mass, and of the depletion time as a function of the stellar mass in the lower panel. You see again results from our simulations are plotted in gray, while different observations for essentially field galaxies are plotted as a different colored lines, so from different recent compilation. And again, you also have plotted the galaxies within the two proto-clusters that I showed you before. And you see that simulations really seems to underpredict the gas fraction for single galaxies. And this is not only true for our simulations, but also, for example, just for comparison, also SIMBA have very similar values of gas fraction. At the same time, the depletion time seems really to be in agreement between observations and simulations, but this is not very surprising, because of course the depletion time or the star formation efficiency is essentially a parameter of our model. So we fix the star formation efficiency to match observations. So it is not very surprising that these two are in agreement one with the other. Okay. So just to see what we have seen until now, we've seen that it seems that simulations fail to reproduce the high values of star formation rate, which are observed in protoclusters regions at redshift higher than 2. And it seems that this is mainly related to difficulty in reproducing the main sequence normalization, but also the distribution of star formation rate values around the main sequence, so the starburst fraction. And while the main sequence normalization seems to be mainly related to the gas fraction, it seems that implementing a more realistic feedback, more realistic stellar feedback can place simulation better in agreement with observational results. The last thing that I wanted to study is there is some dependency on these results from the parameters of our model, so of the star formation and the AGN model. And this is because, of course, we have a lot of free parameters in our model, and we tune them in order to reproduce redshift 0 results. But then, of course, we will have a few degeneracies for the results that we have at a higher redshift. So without going into the details of all this plot that you see here, what we tried was to try to modify different parameters and see the effect on the normalization of the main sequence. So in the next plots, what you will see are the standard run, so our fiducial model plotted as gray points, while the different experiments, let's say, will be plotted as different colored points. So the first thing that we tried was to artificially increase the star formation efficiency by a factor of a few, because we have seen that the star formation efficiency within simulated galaxies is more or less in agreement with observational data, but we have also seen that the position on the main sequence depends on the depletion time. So at least in principle, increasing the star formation efficiency should enable us to also increase the normalization of the main sequence. But if you then see the results, so this is there are the results for the normalization of the main sequence, you see that there are not large differences, and the normalization is more or less the same, and also you don't have much galaxies which are well above the main sequence. So increasing the star formation efficiency seems that do not improve any of the two issues that we have seen before. And this is quite surprising, but the answer, this is due to the fact that the star formation model that we employ is very tightly self-regulated. And indeed, if you see here in the left, essentially this is the star formation efficiency. So the star formation rate at fixed cold gas mass, decreasing the parameter T0, indeed results in a higher star formation efficiency. But at the same time, it also implied that we have a lower gas fraction. So, and at the end, higher star formation efficiency, lower gas fraction results in very similar values of star formation rate. So given that the model is so tightly self-regulated, we try to break this self-regulation. Indeed, this should be possible because we have TC, in this case, is the evaporation timescale. So of course, the evaporation timescale is proportional to the timescale for star formation and inversely proportional to beta and A. We have seen that beta is the fraction of stars, of massive stars, depending on the initial mass function. And of course, more massive stars means also more feedback, thermal feedback, and therefore also lower evaporation timescales. And since A is our parameter that fixes the strength of the thermal feedback, higher values of A means lower values of the evaporation timescales. And if the evaporation timescale in general is longer than the timescale for star formation, then this means that we can consume all the gas in an event of star formation before that the same gas is evaporated. So this should break the self-regulation. And this condition is this one, so the ratio between the evaporation timescale and the timescale for star formation, and this will depend on the density, which makes sense. Higher density also we expect to have stronger, let's say, starburst-like events, and inversely proportional to beta and A0, where A0 is the normalization of the essentially the relation that define A, which by itself is a function of the environment. So in principle, lowering the value of A0 should help single gas particle to reach this condition, so R higher than 1. So evaporation timescale longer than the timescale for star formation. So in this test, essentially, we tried to lower A0 by a factor of 10, so by an order of magnitude. But again, you see that the results really does not show any improvement in what we wanted to do. Even though single particles we checked satisfies this condition, still there are no improvement in terms of starburst and in terms of breaking the self-regulation on integrated star formation rate computed on galactic scales. So the last test that we tried was to essentially to completely remove AGN feedback, which of course is not a very realistic situation, because of course the AGN feedback in simulations is needed, but was to see just roughly the impact of AGN feedback, but again there is no effect on the normalization of the main sequence. The only thing that can be noticed is not very easy from this plot, but you can see it by plotting the galaxy stellar mass functions, that of course without AGN feedback you have more massive galaxies, but this is of course expected since we implement AGN feedback to quench massive galaxies. So I think this is more or less all. Probably finished a few minutes in advance. In any case, apart from the conclusion that I showed you already before, what we can add is that at least within the framework of our star formation model, it seems that both in terms of starburst and also in terms of the normalization of the main sequence, there are not strong dependencies on the parameters of the star formation model and also of the AGN feedback model. So, okay, so thank you for the attention. If there are questions, I'm happy to answer.
Okay, thank you very much. Before I open the floor, I reserve the right to ask the first question myself.
Okay.
So it's actually, well, it's a question / a comment. So it seems that there's a lot of like moving parts in this, right? And you know, often it's like you know, the question is, where does one go wrong, right? Obviously, we're going wrong here somewhere, and of course we can blame the theorists, but maybe we should blame the observers at this time.
Sure.
So there's of course the idea that's in a paper from Deshika Narayanan from, I think it's already some couple of years ago, maybe 6, 7, 8 years ago, where they argued that, where they looked at the gas fractions, right? And one of the things that you showed is that the gas fractions in the observations are higher by factors 2 and 3 compared to the models, right? Essentially compared to all the models that you showed in the plot. And the question is, you know, is that really true, right? It seems maybe, yes, right? The other option, of course, is there might be observational biases, right? So it's possible that this is based on CO observations, right? And in order to convert
not only actually, there are also estimation. Yeah, there are also estimation from the dust emission continuum. But okay, yeah, sure. Also in this case,
there's another set of pictures there, right? So, but I mean, for the CO in particular, the so, and that's the thing, it's a valid point. But so for the CO in particular, there is the issue, right? That so these are calibrated on like nearby observations. And once you go to higher redshift, you have maybe galaxies that are hotter, that have high velocity dispersions, and therefore this so-called X factor, this conversion factor, would be lower, and then you would essentially overpredict the gas fraction. So that's maybe one. Maybe that's the common part of my question. Now, another question is: so what do you think essentially is the kind of data point, either the simulation data point or the observation data point that is kind of suspect? I mean, maybe more than one, but do you have an idea or like a gut feeling where you think one should look that's particularly closely to figure out what is going on here?
Yeah, actually, in this case, for me, it's a very big puzzle because, yeah, of course, there are a lot of assumption needed to derive the cold gas mass. But yeah, I essentially choose these different observational results because, for example, Tacconi uses I think a compilation that employed all the three different techniques that are usually employed to derive the cold gas mass. So in my opinion, I mean, it feels quite strange that using each model, there is a systematic bias on the overall gas fraction. I mean, I of course expect a lot of difference maybe in the scatter around the relation, but a systematic difference for all the observational works feels kind of strange to me, honestly. But of course, it might be. On the other hand, if there is this systematic factor in the gas fraction, then it means that the depletion time needs to be reevaluated, in such case the bottom panel. So at that point, simulation, there will be a tension in terms of depletion time. So we should, since we fix the parameter of our model to match the depletion time, then we should change the parameter for the depletion time, and that maybe will change again the gas fraction in the simulation. So it's, I don't know, it's a little bit difficult to predict what will happen.
Okay, thank you. So we're gonna do it like this. So everyone who wants to ask a question, please raise your hand, and then essentially I give you the word. I see Romain already raised the hand. So Romain, please.
Hi, can you hear me well?
Yes.
Yeah.
So so hi Luigi, a very nice talk. Thanks a lot.
Hi.
And welcome to Zurich, I guess. The question I have is regarding the SIMBA results.
Yes.
And so I just want to check whether I'm understanding this right. So you said that the SIMBA submillimeter prediction is quite close, because the reason was that the star formation rate distribution was correct, right? And
yes.
That's a very clear explanation in my mind. Now I'm a bit confused because you said in the next slides that the depletion time is somehow calibrated on the Koenig-Schmidt relation, right? So but then the gas fraction in SIMBA is way too low. So how come you have the correct, correct normalization of the star formation efficiency?
Yes.
You have the correct star formation rate, but you have the wrong gas mass. I'm confused.
Yes. Yeah. Okay. The explanation that I give myself is that first of all, you see that SIMBA does a little bit better than other simulations, but it is a little bit below in the main sequence. So this. But the main sequence is the median value. This does not mean that the scatter around the main sequence is not reproduced. And the same thing is also valid for the gas fraction. So the median value of the relation is low, but it can be that the scatter around this relation is very high. As if the scatter is very high, then you will also reproduce the high end of the distribution. So maybe you don't match very well the median value, but since the scatter is large, the very extreme situations like strong starburst are quite well reproduced. I don't know. Does it make sense to you?
Yeah. So basically, you're telling me that I should not pay attention to the curves. They are more like very rare peaks.
Yeah, it's like are two different things. One is of course the median, the other is the scatter around it. So maybe one is not very well reproduced, but the other can be very well or maybe overshoot. So the scatter is even larger, and therefore the very high values are you match.
Okay, so it means that the fact that SIMBA matches the high end of the submillimeter number counts doesn't mean the model is correct.
It means that maybe it's better, not completely correct, but it's better.
But better for the variance, but not for the mean. I mean, that's weird. Anyway, I understand the so my last question, the second question, is regarding the AGN feedback, the effect of the AGN feedback that you have shown. I think it's what was your very last slide. I'm very surprised by actually how little effect.
Yeah. Okay. This is another.
From my own personal experience, if I don't use AGN feedback, my stellar mass is a factor of 10 too large. So it moves to the right by 1 dex, right? At least for the most massive galaxy. So here, I mean, look at the upper right point. You have what, 20% more stars without AGN? I mean, it's nothing, right?
Yeah, it's okay. This is not large, but this is also Eiger redshift. So this plot is for redshift 3. So of course, then at redshift 0, you will have much larger differences. And there are also, I don't have here a plot, but because also black hole positioning is quite problematic. In one of our simulations, the black hole goes completely off center. And then, yes, the mass of the BCG is very, there is a large offset.
Okay. Sorry, I didn't get that. It's high. Okay.
Yeah, sorry.
High redshift, I understand. Okay. Yeah.
Yes. And also the feedback actually that we use is not very, very strong, because, well, it's another story, but the fact is that we've seen that either you reproduce the galaxy stellar mass function, or you reproduce the right mass of the BCGs as a function of the halo mass. So in this case, we choose to reproduce the galaxy stellar mass function. In this case, the agent feedback is not very strong. It's much stronger in the other case if you choose to reproduce the correct BCG masses.
Okay, thank you. Makes sense. Thank you.
Okay, thank you. Let's see. Any other questions? Please raise your hand in the chat, in the participants, or I think in the chat window you can do it as well. I don't see anyone. Okay, so let me maybe ask another question in the meanwhile, while you guys are thinking about this. You may be stunned. So we briefly just talked about, right, the sub-millimeter counts, and I think observationally, especially when you go to the high sub-millimeter, and this is actually determined strongly by lensing, right? So most of the object with the high sub-millimeter counts are actually lensed objects. So is this just a maybe quick confirmation here? The data point that you're comparing to the Geach et al., that's de-lensed, is that correct?
I honestly don't know in this case. Honestly, I didn't read this paper, so
okay. Okay. I'm sure they probably do it, right? I mean, it's one of this Lovell paper. Yes. I mean, they wouldn't compare it if it was. I mean, it's not so easy to do the de-lensing, that's what I'm saying. But so there are probably kind of additional good uncertainties. But if it was not de-lensed, then obviously you would totally expect the simulations underpredict the.
No, honestly, I don't know. I just know that for the simulation they took into account blending, but apart from that, I don't know if lensing for the observational data.
Okay, thank you. I see a question by Andrea. Andrea, please go ahead.
Yeah, I was wondering, just a simple question. Do you see a connection, or maybe a causal connection or delay between the AGN feeding and starburst in the simulations?
Honestly, no. No, definitely no causal connection between high values of star formation rate and AGN feedback, just the opposite, so quenching. But for increasing star formation rates, no correlation.
Thanks.
Okay, any other questions? Luigi, so you looked at essentially physical parameters, right, in this talk: star formation rate, stellar masses, gas fractions, and as I think as I would alluded to in my first kind of comment / question, this can be difficult sometimes to do, right? Because of course this means that we have to convert observational data into physical quantities, which comes with a large uncertainty associated with it. Have you also tried to see how well your simulations compare to more directly measurable observational quantities, like say color magnitude diagrams, or just the color distributions of your simulated galaxies, etc.?
No, honestly, honestly, we didn't. Yeah, actually, I followed talking with my supervisor. Essentially, you have two options. Either you trust observations and you trust what you're doing, or you make assumption to simulate what observational studies do, but then you have also, of course, uncertainties given the procedure that you use to mock the observation. So yeah, at the end we decided to just use output of the simulations as it is, and trust what observers do. Yes, so we didn't try to compare with that.
Okay, thank you. Okay, any other questions? Okay, well, then, yeah, if there are no more questions, I mean, Luigi is of course around. Feel free to send him an email and ask him about his research. I also want, obviously, also like to welcome you here to Zurich. It's going to be exciting to work with you together in the future. Okay. Okay. Thank you very much, everyone. That was today's astrophysics seminar.
Bye-bye.